Okay, welcome back everyone. This is lecture 22. I'm going to be trying a slightly different format that hopefully works for more people. A lot of students were telling me that they had trouble viewing those videos that had two screens overlapping with each other in the last lecture or two. Okay, so we're going to continue in this lecture talking about rotational motion and focusing on problems that involve torque and angular momentum. Okay, so to get started, this slide shows some sort of overview of the kinds of problems that we deal with when we're talking about torque and angular momentum. And they all these different approaches here, should be 1, 2, and 3, stem from or can be derived from this basic relationship of the torque being equal to the change in momentum with respect to time. So the tau being equal to dl dt. So that is going to be useful in problems like this point number 1 here, where in the case where the net torque is 0, so the left-hand side of that tau equals dl dt equation is 0, in that case, then, so like I'm saying here, these problems all stem from this basic fact. The torque equals a time derivative of angular momentum. So even if you're not super comfortable with time derivatives and calculus, the first type of problem we're going to be dealing with here on the slide is the kind where tau, or the net tau, is 0. In that case, this means that there is no change in L with respect to time. That is, L is constant. In that case, this is like in previous problems where we considered conservation of momentum, linear momentum. This is what happens when you have conservation of angular momentum. For linear momentum, it was the case that whenever the net forces on a system were 0, then momentum was conserved. And here we have whenever the net torques on a system are 0, then angular momentum is conserved. Okay, so that's one kind of problem, and we're going to do an example related to that. A second kind of problem is with statics. So that is, statics, as it sounds like, is a type of problem where we're not considering movement. Things are not moving, and the forces that are at play and the torques that are at play in the problem are balancing each other. So for statics, we still have a case where tau net is 0, but in this case we also have no motion at all. In this case, the torques in the problem, or the forces in the problem, are all sort of pushing against each other in just the right way so that nothing moves. There's an example in the book about a ladder leaning against a wall and not falling down. That's a case where the ladder's got various torques and forces on it, but it's not moving. And we'll do another example in this lecture where the forces and torques balance out and there's no motion. And then a third type of problem is when there are, in fact, there is a non-zero net torque, not like these cases. The tau net is not 0, so the net torque is not 0 in this case number 3. And if that's the case, then you will have some angular acceleration. Just like when F equals ma, if tau is not 0, then tau equals I alpha, where I is moment of inertia and alpha is angular acceleration. Okay, so in these kinds of problems, we'll do an example of that too. In these kinds of problems, we need to figure out things like what's the angular acceleration and whatnot. There is motion for sure in these kinds of problems. All right. So a number of you told me that you had some difficulties with MC homework 20, and the problem that was being used in that multiple choice homework problem, which comes from figure 9.3 in the book. So I've recreated a sketch of that figure here on this slide. The situation that you're supposed to imagine is that you have a particle that's being represented by this red dot moving towards the orange bar. So the particle is the red dot in the upper left. It's got an initial velocity of 3 meters per second, and it's flying along on a straight line towards the end of this rod, the orange line in this picture. The other end of the rod, the end that's not going to get hit by the particle, is attached to some sort of pivot so that the rod can spin around that pivot point. That's indicated by the dark dot at the other end of the rod. The length of the rod is certain. It's 1.5 meters in this problem, and initially the rod is at rest. So just to clarify one more type of potential confusion, in this problem there's no gravity to worry about, so you shouldn't be thinking about gravity pulling the rod downward or anything. Maybe you could imagine this as us looking down at a rod that's in a horizontal plane, and in that case its motion doesn't get affected by gravity. So before the collision, you have the particle speeding towards the rod at 3 meters per second. After the collision, what we imagine is that the particle keeps on moving on that straight path, has a new velocity, Vf. It's given up some of its initial kinetic energy, so Vf is going to be less than Vi, and that kinetic energy that it gave up was given to the rod when it collided with the rod. So it hit the rod. Now the rod is spinning around in a circle attached to that pivot point again, and it's spinning around at an angular velocity of omega f. Okay, so some of the questions, I'm not going to go through all of that MC20 problem, but let's go through a little bit of it. Okay, so first off, let's try to figure out what is the angular momentum of the system. So let's review some facts first in order to answer that. Okay, so first, let's think about what are the external forces and external torques in this problem. So on the slide, I'm showing you a sort of before and after picture of the collision. During the collision, let's consider what's going on. So during the collision, we have the rod, the pivot, and the particle that smacks into the rod making contact with the tip of the rod like that. Okay, so so first of all, make sure you realize that the interaction between the particle and the rod are not external forces, right? The system that we're considering here consists of the particle and the rod. So the interaction between the particle and the rod, the forces that happen up here during the collision, are not external forces, those are within the system. The only external forces that are existing in this problem come from the influences of this pivot, right? If the pivot was not there and the particle hit the rod, it would fly off spinning in some way. But in this case, because of the pivot and the forces that the pivot provides, the rod is forced to only move in this rotating around the pivot motion. So the external forces are not zero. Those are the forces due to the pivot. On the rod. So those forces are not zero. But the external torques, on the other hand, external torques, at least if you're going to consider torques relative to a origin that's located at the pivot. So we consider our origin right here. So this is relative to the origin, these are equal to 0, so there are no external torques. And why is that, right? There are forces acting due to the pivot, but no torques. How can that be? Well, if your origin is right at the pivot, then if you remember, so recall that torque is equal to R cross F. So in this case, here in this problem, R has 0 magnitude. That is, the point at which the force is acting on the rod is right here at the pivot, and the origin is right here at the pivot. Therefore, the position vector that locates the point where the force is acting has length 0. Therefore, the magnitude of tau is 0. Remember, it's R, magnitude R times magnitude F times sine of the angle between R and F. So if R magnitude is 0, then tau is 0. Okay, because of that fact, this fact, that implies then that L is constant. Angular momentum is a constant. Keep in mind, in this problem, not that we're going to keep track of it in this problem, but the linear momentum of the system is not constant because the external forces are not 0. Remember, that's the condition for fixed or conservation of linear momentum, is that the external forces have to be 0, which they're not in this case. But angular momentum is constant because the external torques are 0. All right, so if we try to answer this first question then, question 1, which was what is the angular momentum of the system? Because L is constant, we can calculate L at any time during this process, before, during, or after the collision. Whatever time is the easiest to calculate it, we can calculate it. And because L is not changing, you'll get the answer, the same answer, no matter when you calculate it. So you might as well pick a time or a point during the process that's easy to calculate. So let's choose the time right before the collision. Remember, any time would be the same, so we can choose the time that's most convenient for the calculation. So right before the collision, again, the picture looks like this, like I just drew here. You've got the particle, and here's our origin, and the distance, so the position vector of the particle. So if we're right before the collision, the rod still has 0 motion, so the only angular momentum to consider is that of the particle. So L total, you could think of it this way, equals L particle initial plus L rod initial, and this one is 0 because the rod is at rest. This one is not 0, so if we calculate this, we know the total momentum, angular momentum, and that's what the total angular momentum is throughout the collision, before and after and during, because of conservation of angular momentum. Okay, so to calculate this, the angular momentum of the particle initially, right at that moment before the collision, we need to do this cross product, R cross P, where P is its linear momentum. Remember, it's moving this way. So P equals mv for this particle. And for this problem, if you remember, it's written on the slide here, the mass of the particle, I didn't write that on the slide, the mass of the particle was 2 kilograms. That's what it was in this problem. So P is going to be 2 kilograms times 3 meters per second, and it's to the right, in that rightward direction. Okay, so R cross P, right? R is pointing in this picture straight upward, P is straight to the right, so there's a right angle between the R vector and the P vector. So, when we calculate this cross product in a moment here, we will calculate it like this, right? This is the formula. Magnitude R times magnitude of P times sine of the angle between them. What's the angle between them? In this case, remember you translate the two vectors such that they are tail to tail. So the R vector is pointing up this way. That's R. And there's a right angle between them. So this is sine of 90 degrees for us in this problem. So sine of 90 is 1. So, and R equals 1.5 meters. So this is to the right. This is up. I didn't draw x, y coordinate systems here, but that's the directions of these vectors. So L is equal to the magnitude of R, that's 1.5 meters, times the magnitude of P, which is 6 kilogram meters per second, and times sine of 90 degrees, that's 1. So this is just 9. Okay. That's the answer for that first question. And remember, it's true for all times, even if I calculated it only at this point, this time when it was very convenient to do so. Okay, what about question number 2 here? This is one where I think people got tripped up more and had more difficulties on the multiple choice homework. So for question 2, you are asked to find out what is the kinetic energy of the rod after the collision. Okay, so to answer that, this is K final of the rod. That's what we're trying to get to for question 2. So a fact that was initially not listed in the problem, and I corrected that, is that this is an elastic collision. It was kind of implicated that this is an elastic collision in the book where they were talking about this problem, but it wasn't really explicitly stated. But anyway, this is a fact of this problem, that it's an elastic collision. And that means that energy is conserved. So, in other words, in this problem, since there's no potential energy to think about, remember I said there's no gravity that's pulling the rod down or anything like that, this means, since there's no potential energy to worry about, that the K initial is equal to the K final. So if you can figure out the initial kinetic energy and the final kinetic energy, that can probably eventually get us to the final kinetic energy of the rod. Maybe this should be KRF or something like that. So the final kinetic energy, KF, so maybe we could write this down. KI first. That's just going to be K of the particle initially plus K of the rod initially. And like we already said, this is 0 because the rod's not moving initially. So initial kinetic energy, we just have to figure out based on the particle. And the particle was 1/2 mvi squared. The particle was moving at 3 meters per second. So this is 1/2 2 kilograms 3 meters per second squared. That's equal to 9 joules. Okay, what about K final? That's going to be K final for the particle plus K final for the rod, right? Those are the two parts of the system to worry about. And so for the particle, again, it's going to be 1/2 mv squared, but this time it's v final, which we weren't given that information in the problem. And for now, I'm going to leave this alone. I'm not going to write an expression for k final for the rod. You could do it. It's not impossible, but it is tricky to write down an expression for this. It involves the rotational kinetic energy and the translational kinetic energy. So it's difficult to write down an expression that's correct for this. So what we're going to do to find out the answer to what this is, that's our goal, is we're going to figure out what this is, set that equal to this, and then solve for KRF. That's the plan. Okay, so what's V final? Now here, I'm not going to do all of the derivation from the book. We had an equation that was derived in the book, equation 9.8, which said that V final in this problem was 3m minus, that's little m, that's the mass of the particle, that's big M, the mass of the rod. So 3m little m minus big M divided by 3 little m plus big M times V initial. So this expression, you can read the book and see how it was derived. And it's derived based on using energy conservation and angular momentum conservation. But I'm not going to repeat that derivation here. So if we plug in the numbers we have, the mass of the particle is 2 kilograms, the mass of the rod is 5 kilograms. So the numerator here is 6 minus 5, that's 1. The denominator is 6 plus 5, that's 11. And VI was 3, so this is 3/11 meters per second. That's VF. Okay, so let's go ahead and set KI equal to KF, that's energy conservation. That implies then that 9 joules equals 1/2, so I'm going to plug in 1/2 mvf squared here, so that's for the particle, that's 2 kilograms the mass. VF, we just figured out, is this 3/11 meters per second squared, plus KRF, that's the kinetic energy of the rod that we're looking for. So go ahead and calculate that number, move it to the left-hand side of the equation, subtract it from the 9, and what you'll find is, let me look at my notes here, this is 8.93 joules. That's how you solve this problem in the easiest way. Okay, so those are the examples that I was going to go through for problems related to conservation of angular momentum. There's one of your open response homework problems coming up that's somewhat similar to this as well, so hopefully that will help you get through that problem. Okay, so next thing I'd like to talk about are statics problems. And one of the important aspects of doing statics problems, so these problems typically involve some extended body, not a point, but some kind of extended body. Like in this slide, there's two kids on the ends of a teeter-totter, and to understand how things are moving or how they're not moving in a statics problem, you need to be able to draw one of these slightly more complex force diagrams. So you got to keep track of all the forces and where they're acting on the body. So in this case, in this slide, the force of the boy on the whatever this thing is, the seesaw is on the left of the diagram, and the force of the girl on the seesaw is on the right part of the diagram, and gravity is acting downward. And you can always represent gravity as acting on the center of mass because it's acting the same all along the length of this rod. So the gravitational force ends up effectively behaving as if it's only acting on the center of mass. There's a more detailed derivation of that in the book that you might want to look at. And then there's going to be a force upward due to that red support device that's indicated by that upward force arrow in the center there. So keeping track of forces and force diagrams, you need to be careful and put the forces in the right places along the solid body. Okay, so let's do an example problem where that kind of a thinking is relevant. So this one is a problem where we're thinking of balancing two weights at either end of a sort of a teeter-totter, but it's imbalanced, so the supporting point is closer to one end than the other. So imagine you have a 1 meter distance between the support and a mass that I've labeled A, and a 5 meter distance between the support and a mass that I've labeled B. And we're going to assume that the length of that thing that A and B are resting on has no mass, or it's a small enough mass that we're not going to worry about it. Okay, so if the what we're going to consider is a balanced situation, right? If this is perfectly balanced, then nothing will move. That is, if A is heavy enough, right? Probably your intuition is telling you that this is going to tip to the right if these two things are the same mass, right? The B side is going to fall down. But if A is heavy enough, then it will be balanced. So we're going to try to do a simple calculation to figure out exactly what the forces need to be in order for it not to tip. So if it does not tip, that means that the torques must be canceling each other. Okay, so let's go ahead and do this problem. So here's our balance thing. Here's block A, block B, and we said that, oh, okay, it's always important in these problems about torques and angular momentums to define your origin. And it's always a good idea to put that definition of the origin at the rotation point. If there's rotation about a particular point, in this case it would be about this support point. For that case with the rod spinning, it was about the pivot point of the rod. You always want to put your origin at the point of rotation. Okay, so here's the origin right here. And that means then that the torque on block A is going to be given by the force on block A, which in this case we're imagining gravity, so that's going to be ma times g pointing downward. So that torque is, remember, Ra cross the forces on A. That's the general formula for how we would write the torque on this side. And what's Ra? That's the position vector from the origin to block A. And the way it's been drawn here, with this being perfectly horizontal, this vector Ra is again perpendicular to the force vector. That is, if you move this one tail to tail, then the position vector would be here, and that's a right angle between the position vector and the force vector. So Ra cross Fa is going to be magnitude of Ra, which is 1 meter, times magnitude of the force, which is, I said mass A has 10 kilograms here on the slide, so it's mg, right? It's 10 kilograms times 9.8 meters per second squared, and that's then times sine of the angle between them, 90, which is 1. So this is, 98 Newton meters. Force times the distance of Newton meters. And the direction of that vector, if we follow what we learned before, it would be pointing up out of the page. But in this case, the direction doesn't matter too much for how we're doing the problem. We just need for this torque to be equal and opposite to that torque on block B. Block B has a force, gravitational force, also pulling it downward, and the magnitude of that is mb times g, and its position vector rb has a length 5 meters. So go ahead and write it down. 5 meters, that's the length of the position vector, and the magnitude of the force vector is going to be, again, mb times 9.8 meters per second squared times sine of 90. Oops, sine of 90 degrees. And that's, again, 1. Right, this force vector and the position vector are right angles to each other, again. Okay, now, this is the point. So we don't know what MB is. That's what we're trying to figure out. What mass does B need to have in order to balance the mass of A so that this thing does not tip over? So that means that we have to set, the torques have to be canceling each other. So, let's see here. I said the signs of the torque didn't matter. I'm going to take that back now. So let's keep track of them. So the sign of the torque, or the direction of the torque for A is, let's see, put your fingers in the direction of R, cross F, finger pointing out of the page. So this is out of the page, pointing up this way. And we need this one to be pointing downward. So R is in this direction, force is in that direction, the torque is in that direction. So they're opposite in sign to each other. So what we have then, since they're opposite in sign, we need to use a minus 98. So let's see, what am I doing here? I'm saying that tau A plus tau B has to be equal to 0 for no tipping. That's what I'm saying. So the net torque has to be 0 in order for this thing not to tip. So I'm going to set the 98 equal to this thing, but there's a sign difference because the two torques are pointing in opposite directions. So minus 98 has to be equal to, well, I think we don't need that sign. Let's see, 5 times 9.8 times MB. I'll take care of my units in a moment here. Solve that for MB. That's going to be in kilograms. So that is 98 divided by 9.8 is 10. 10 divided by 5 is 2. That is 2 kilograms. So MB has to be 2 kilograms if it's sitting out at that further distance of 5 meters. Okay, what about if we tilted it? Right, if you tilt this thing to start with at some angle, so let's put it at some angle, and that angle, so relative to some horizontal, that angle theta is 30 degrees. We're saying theta of 30 degrees in this problem. What if you tilt it? Is the mass of B still the same, or does it need to be some different value? So again, we're going to balance these things. So what's the tau A? That's going to be equal to, I'm just going to skip ahead a bit. It's still the same kind of calculation, but it's 1 meter times 10 kilograms times 9.8 meters per second squared times sine of, this is the part that gets important, it's not theta here, be careful. So the force is this direction, the position vector is this direction. So if we put them tail to tail, this is the position vector. This is the angle we're worried about for sine of an angle here. What is that angle? So this, maybe draw a horizontal line here, this will help. There's a right angle between that horizontal line and the force, the gravitational force, and this angle is 30. So we have 90 plus 30, that's 120. That, if you take sine of 120 degrees I looked it up a moment ago, is 0.866. Okay, let's see what is tau b. If we keep the mass the same, let's see what it is. So we have 5 meters. Let's just leave it as MB for now. 9.8 meters per second squared. Sine of, what's the angle here? So now the force vector is still pointing straight down. The position vector is that vector, which if you put it tail to tail with the force vector, so this is the position vector, r cross f. This is the angle between the r vector and the f vector, which is, if you look at the geometry a bit, you'll see that this angle's 30, so this must be 60. Again, the gravitational force is pointing straight downward, so it's at a right angle with the horizontal. So this is sine of 60 degrees, which is, turns out, exactly the same value. It's 0.866, right? So it turns out that now if you set these two things equal to each other, tau A equals tau B, then these two values cancel each other. So it does not matter that it's at a tipped, it's not, if it's tipped, it's still going to be the case that MB has to be 2 kilograms in order for them to be balanced. So the tipping does not matter. Okay. So next, we're going to talk about a type of dynamics in these problems. So the type of dynamics that we're going to talk about is rolling, and rolling without slipping in particular. So lots of rolling that happens without slipping. For instance, the wheels of your car hopefully are not slipping and they're rolling along the road surface. Bike wheels, lots of things roll without slipping. Okay, so in the case of rolling without slipping, we're going to build up some tools here. These ones are also developed in the textbook. So on this slide, the point that I would like to make is that if you want to keep track of the center of mass speed, so again, we're going to imagine something round rolling along in this direction. So it's actually rolling this way. So if you keep track of the center of mass position, it's this point, it's going to be moving in this direction, and it's going to have some center of mass velocity. So how fast does the center of mass move? Well, we're going to relate that here. So what I'm going to show you is that is equal to r times omega, where omega is the angular velocity about the center of mass. So remember, omega, any of these rotational quantities, omega, alpha, the angular acceleration, angular momentum, torque, all of these have to be specified with respect to some point. So here we're talking about the center of mass as the point of reference. So the angular velocity about the center of mass is omega, and r is the radius of the thing that's rolling, and the center of mass velocity is equal to r omega. And the way you can imagine that, I find easiest to imagine it, is if you do one full rotation. So you roll the wheel until the same point comes back to being in contact with the ground. That means the distance that it rolled, as indicated on the slide here, is the circumference of the thing, which is 2 pi r. And that's how far the center of mass has moved. So when this thing rolls through a full turn, then the distance the center of mass has moved is 2 pi r. And in general, if you move less than that distance, you roll through an angle that's less than 2 pi, say just delta theta, then what's written here, r times delta theta divided by delta t, is going to give you the center of mass velocity, right? So in r times delta theta over delta t, in the limit of small delta t is omega. So that's how this expression comes about. Okay, so that's one important expression. And maybe before I move on too much here, you can take this expression and just take a time derivative if you want, and you can get that the center of mass acceleration, so how fast this acceleration is, the center of mass is accelerating to the right, would be r times the rate of change of omega, and that is what we call alpha, the angular acceleration, right? So there's this relationship between angular acceleration, alpha, and linear acceleration of the center of mass. That's just proportional by this factor of the radius. Same for the angular velocity. Yeah, same for the angular position, to be honest. So if you want to know the position of the center of mass as it's moving along, that's r times theta, where theta is the amount that it's turned. Okay, so another point that's on this slide that I'd like to point out is that the velocity of different points along the rim of the rolling thing are different, as you might imagine. So one of the most important points is that the point of the rolling thing that's in contact with the surface that it's rolling on, the Earth, for example, is 0 relative to the Earth, the surface. Right? It's not slipping. That's what it means to be not slipping. To be rolling without slipping means the point of contact has 0 velocity instantaneously. As soon as it leaves that contact point, then the velocity of that point becomes non-zero. The center of mass of the rolling thing is moving right along, right? That's why a car rolls forward and whatnot. But the point of contact is not moving. Because of that, there's a static friction that is important in these problems of rolling without slipping. The static friction is always acting at the point of contact between the rolling thing and the surface it's rolling on. So this is the last example I'd like to do today in this lecture, which is an example of rolling down an incline. And we're going to ask, if the only force is gravity, you've got something rolling down an incline with an angle theta, we're going to ask how quickly does it accelerate? What's the center of mass acceleration? We're going to use this equation here that I just wrote down as part of how we get that answer. Okay, so let's see, maybe I can start by considering, okay, so redraw it maybe. Instead of talking about a flat surface, we've got a tilted surface, and the angle that this tilt has with respect to horizontal is theta. And we have our rolling object that's rolling down this surface. The only forces that are acting, well, there's 3 forces acting as it's shown on the slide here. There's gravity, which pulls downward. There is a normal force that acts at the point of contact here. There's a normal force pointing that way. Remember, normal forces are always perpendicular to the surface. And then there is a force of static friction that I'll call F superscript S that is resisting slipping, right? So if you want to know which direction this force points, you can imagine how this thing would slip if this was a frictionless surface, right? It would slip down the surface. So this force has to resist that slipping motion, so it has to point up the direction of the surface. Okay, but we've got all these forces pointing in different directions. The only ones we need to keep track of, really, in order to figure out the answer to this question, how fast does the cylinder accelerate down the ramp, are the ones that are along the direction parallel to the slope. So let's write down the forces in the x direction, and we'll call this the x direction. Normal force would be in some, say, the y direction. So the normal force has no component in the x direction. The only forces in the x direction, let's write this F net x equals ma center of mass. Okay, so what are the net forces in the x direction? Well, there's one that's Fs, that's going to be in the negative x direction. And there's a component of gravity that's also in the x direction, the positive x direction. And that is going to have, you might have to think about the geometry a bit to convince yourself, but this angle is theta, same as that angle. So that the magnitude of that gravitational force along the x direction is positive mg sine theta. So that has to equal to the mass times the acceleration of the center of mass. Okay, another thing we're going to keep track of in this problem that will be useful are the torques. About, again, if you talk about torque, you always have to say about what point. So about the center of mass. So this point is the center of mass. So the torque's about the center of mass. And like I wrote on the first, one of the first slides here, this is one way to write that similar thing to Newton's second law in terms of rotational motion. You say the torque is equal to I alpha, where I is the moment of inertia, alpha is the angular acceleration about that center of mass point. Okay, so the torques, remember, gravity always you can consider as acting on the center of mass. So the point at which it's acting is at the center of mass. So there's no torque due to gravity because it's at zero distance from the center of mass. The normal force is acting at this point that's away from the center of mass, but it's pointing directly towards the center of mass. So the angle between the position vector and the normal force is 180 degrees, so that will have zero torque. The only thing that contributes to torque is this frictional force. And that is going to be, so the left-hand side here, the net torques are going to be minus Fs times r, if the cylinder here has a radius r. So this is the position vector from the center of mass to the point of the force acting. Here's this friction force. There's a right angle between them. So it's just the magnitude of this force times the magnitude of the position vector, which is r. That's here. That's what the torque is. Okay, let's keep going. That's some information we need to this problem. All right, so let's put some of this together. So we're going to use this fact. Let's call this equation 1 here. This is going to be equation 2. Oops. And this is equation 3. We're going to put these three equations together. 1 and 2 and 3 are what we're going to put together in order to calculate the center of mass acceleration. That was our goal here. Okay, so I'm just going to, okay, let's go for it. ACM equals r times alpha. And I'm going to use this to substitute in for alpha minus FR and Fs times r over I. Right, if you solve this equation 3 for alpha and you plug it in here, I think I need a sign here. So this is correct the way this is written, but the sign conventions in these rotation problems is always, it's a kind of up to the person doing the problem, but in our book the convention is that if you have clockwise rotation, that's a negative sign. So the alpha here is negative in the sense that it's clockwise rotation. So we get two negative signs here that kind of cancel each other. So that is Fs r squared over I. So now we're going to plug in what we know. So if we solve equation 2, for Fs, that gives us Fs equals mg sine theta minus m a okay, and then we plug that in for Fs, right? So we have ACM equals this stuff, mg sine theta minus MACM times r squared over I. Now we just have to solve this for ACM. Everything else are constants in the problem, like the mass, g, the angle. I is determined by the shape of the body, so is r. Okay. So let's move this over here. Got mr squared over I times ACM. That's moving this term to the left-hand side of the equation. And this is mr squared over I g sine theta. That term stays on the right-hand side. Okay, so that means ACM, factor that out of these two pieces. Oops. We're almost there. Looks kind of messy, but it's not bad actually. So ACM, if you divide both sides by this piece, you have a formula. You might neaten it up one more step. If you divide the top and the bottom by this mr squared over I, you would have g sine theta over I mr squared plus 1. That's an answer that we could work with. We could, for a given theta that we might have in the problem, for a given shape of the body, an I and an m, we could go ahead and calculate what's the acceleration of the thing rolling down the ramp. It might be interesting to note here too that, right, if this was just sliding without friction, we know the acceleration would be g sine theta, right? The force is mg sine theta. And if there's no friction to make this thing roll, then the acceleration will just be g sine theta. So this thing in the denominator is how the acceleration changes due to the rolling. And you can probably see that this denominator is going to be bigger than 1. Why is that? Well, if you look at all of your formulas for I, for various things like cylinders and spheres and things, it's always some fraction, like 1/3 or 2/3 times mr squared, right? So if I is, say, 2/3 mr squared, then this ends up being 2/3 right here, plus 1. So you get this denominator that's always something bigger than 1. So your acceleration as this thing rolls down the ramp is always going to be a little less than it would be if there was no friction, if it was just sliding. Okay, I think I'm going to stop there for this lecture. See you next time.